In this video, we're going to continue with our example of simultaneous multiple regression, moving from the ANOVA and model summary tables to the coefficients table. Now, here's a complete coefficients table, but we're not going to address these correlations at the end until a little bit later, so let's kind of drop them for now and slide things over to give us a little bit more room. And remember, from our ANOVA table, our degrees of freedom residual was equal to 395, because we're going to need that in just a minute. Now, looking at this output and thinking back to some of our previous videos, what's the result for school quality focusing on the unstandardized coefficient? Well, the formula for t is that it's b, the unstandardized coefficient, divided by the standard error of the regression coefficient. So in this case, that's 0.042 divided by 0.017, which is 2.453 using non-rounded numbers. And remember, we have the 395 degrees of freedom that we'll use for our t-test, those residual degrees of freedom from the previous video, right? So we would write this up as b equals 0.042 with t with 395 degrees of freedom equal to 2.453 and a p-value of 0.015. Now, assuming our alpha level is 0.05, we would reject the null hypothesis that the effect of school quality is equal to 0. It does look like it's having an effect on GPA, controlling for all of these other variables. Now, what about mother's education? Why don't you pause the video for a moment and see if you can provide the same summary, but this time for mother's education, okay? What'd you get? Okay, our result for the unstandardized regression coefficient for mother's education would just be b equals 0.113 with a t with 395 degrees of freedom equal to 5.551 and a p-value of less than 0.001. And again, we would reject the null hypothesis that the effect is equal to 0. Mom's education does seem to be having an impact on GPA, controlling for the other three variables. Now, our regression coefficients are point estimates of their corresponding effect. That value of 0.113 for mother's education is our exact estimate of what we think the effect for mother's education is out there in the entire population. But of course, we only have a sample from the population, so our estimate is almost certainly off at least a little bit. And that's where the confidence intervals come into play. They give us a sense of the precision of our regression coefficient, the precision of that point estimate. The regression coefficient gives us our best estimate of the specific population value, but we're also confident that the true population value is somewhere else. It may be very close to that point estimate, or it might be anywhere in a broad range of scores around that point estimate. Kind of which is it? And that's what the confidence interval tells us. Now, technically, the 95% confidence interval indicates that if an infinite number of people all did the same study with different samples, and they all calculate their own 95% confidence interval for mother's education, based on those confidence intervals, the 95% of these 95% confidence intervals would in fact overlap the true population value. But you can think of the confidence interval as telling you how precise, how accurate our value of 0.113 is. In this case, you can think of this as indicating that while our specific point estimate for the effect of mother's education across the population is 0.113, we're 95% confident that the true population value is somewhere between 0.073 and 0.153. Now, for a little review, remember, we calculate the 95% confidence interval by taking the regression coefficient and adding and subtracting the product of the critical t-score that bounds 95% of the distribution times the standard error of our regression coefficient. And remember, don't use the t-score you obtained in the t-test you just did. Use the critical score instead. So if you're doing this by hand, we first need to look up the critical t-score that, again, bounds 95% of the distribution with 395 degrees of freedom, right? And if we look that up, we see that the critical t-score is 1.966. Now, a 95% confidence interval would be our regression coefficient, B, or 0.113, plus and minus our critical t-score of 1.966, times the standard error of 0.020. If we multiply 1.966 times 0.020, we get our 95% confidence interval equals 1.13 plus and minus 0.040, or our 95% confidence interval equals the range from 0.073, that lower limit of the confidence interval, up to 0.153, the upper limit for our confidence interval. And of course, if you're doing this by hand, your values will be slightly different due to rounding, and that's okay. Now, I think it helps to visually see what's happening here. So let's take a look at what these numbers are really telling us. Now, remember, the regression coefficient is a slope. You can think of it as a slope for a line in this illustration, even though we know from previous videos that it may be the slope of a whole multi-dimensional surface, right? But thinking of it as a line will work for now. So if mother's education has no effect, what would be the slope for the line? What would be our regression coefficient? Well, it would be 0. It would be a flat line, right? It doesn't matter what the level of mother's education is, there's no effect. But our regression coefficient, our estimate of the effect, was not 0. It was 0.113. We think there's a positive association. More mother's education is associated with higher grades for her kids. But that's just an estimate. We know it's not going to be exactly equal to the true population effect for mother's education. The confidence interval reflects the range of values for this slope, where we believe the true value for the entire population lies. Now notice that that red line we drew for our no effect is outside of the range for our confidence interval. The confidence interval does not contain the value we expect to see if the null hypothesis is true. We're 95% confident that the true population value is somewhere in that confidence interval, and the no effect null hypothesis value is not in that range. That means we're also 95% confident that the null hypothesis value is not true. This is why an alpha of 0.05 and a 95% confidence interval will lead to the same conclusions regarding whether to reject or fail to reject the null hypothesis. Now, let's calculate the 95% confidence interval for study hours. Our 95% confidence interval would be our B, or 0.024, plus and minus the same critical t-score of 1.966 times the standard error of 0.017. If we multiply 1.966 times 0.017, we get our 95% confidence interval equals 0.024 plus and minus 0.033, or our 95% confidence interval equals the range from negative 0.010 up to positive 0.057. Let's visualize this as well. Now, here's our slope of 0, that null value we would expect to see if school quality had no effect. In this case, our B was 0.024, right? And our 95% confidence interval ranged from negative 0.010, slightly negative slope, up to a positive 0.057, right? Now, notice this time that red no effect line falls within the range for our 95% confidence interval. What does that mean? What does that tell us? Well, ask an angry Willy Wonka.
You get nothing. You lose.
Take it from Willy Wonka. If the confidence interval contains the null value, typically B equals 0, you know you will fail to reject the null hypothesis. Now, on that note, why don't we wrap up this video here? In our next video, we'll look at semi-partial correlations and unique variances. Okay? Bye for now.